So today I would like to present to you some work that I have recently done in collaboration with colleagues from the Ruhr University in Germany, in Bochum, and from the GFC Potsdam. And it addresses the conditions for aftershock seismicity after the Tohoku earthquake. The Tohoku earthquake in 2011 occurred offshore northwestern Honshu of Japan, and it was probably one of the most intense megathrust earthquakes that have hit Japan within the last centuries. One particular of the Tohoku earthquake located on the plate boundary fault or megathrust at about 20 kilometer depth. And one particularity of this earthquake was that it ruptured the entire megathrust up to the deep sea oceanic trench, and which caused very high slip close to the trench. The Tohoku earthquake also caused a lot of aftershock seismicity, of course, along the actual plate interface, but also within the overlying forearc wedge, which is here indicated as North American plate. And in my talk today, I will address the conditions for the aftershock seismicity within the forearc, but not only for the marine forearc that you see here, but also for the onshore part of the forearc from the island of Japan. So here you see another map of northwestern Honshu. This is a coastline outline. The red star here indicates the hypocenter of the Tohoku earthquake. And then you have this pink contour lines, which mark slip contours. And you see we have the main slip patch here, offshore Sendai. And this is what I mentioned before. We had up to 60 meters or even more slip very close to the trench. Then you see we have also a southern slip patch, which is this one here, offshore Iwaki. Then we don't have this intense slip close to the trench, but we had some 10 to 15 meters of slip at intermediate depths on the plate boundary. And then you see all these mass here, all these colored dots. And these are aftershocks that locate within the forearc. They are, the color indicates the hypocentral depth. And you can see they affect a very broad region of this forearc here. And this aftershock seismicity initiated directly after the Tohoku earthquake. You see here a timeline indicating the seismic activity before the earthquake and then after the earthquake. And you can see that there is a sudden increase in seismicity, which is then roughly exponentially decaying. But if you look nowadays, the seismic activity in Japan, 11 years after the earthquake, there's still a higher seismic activity than it was before the earthquake. This increase in aftershock seismicity, you can also see if you look at cross sections. These are 200 kilometers wide swath profiles that project the seismicity into a vertical cross section. And this shows now for this northern profile here, offshore Sendai, crossing the main rupture area, the seismicity before the Tohoku earthquake. This is from 2008 to 2011. And what you can see is there's very little seismicity close to the plate interface, probably along the plate interface. We have mainly thrust faulting events that are also likely events on the plate interface. And then we have some additional seismicity in the onshore part of the forearc. That is the seismicity that you would locate here within the arc, in the volcanic arc region. And this shows now the situation after the earthquake until the end of 2011, that are approximately 300 days after the earthquake, integrated over 300 days after the earthquake. And you see that we have all these little gray dots. That is now a massive increase in the seismicity, affecting large volumes of the forearc. And you see all these blue beach balls that indicate non-fault. So we had in the submarine part of the forearc all these non-faulting events indicating that there was a tensional stress condition. Then there's also this trend of little seismicity that reaches up here into the onshore part. But here you see we still have reverse faulting and compressional strikes in fault. The same picture or a similar picture is if we look at the southern cross section that is now indicated here. This is the Barkey transect that crosses the southern slip patch. We have again very little seismicity before the earthquake, some thrust faulting in the onshore part, and after the Tohoku earthquake, you see all this intense seismicity within the forearc. This area here is close to the coastal area of Ibaki, which is the biggest city in this area. And you can see this actually occurred onshore. So it gives you a similar picture than for the north, but actually we have here in the south the even more intense aftershock seismicity, which really reaches also into the coastal regions. If we summarize that up all together, we have comparatively little aftershock seismicity onshore and intense aftershock seismicity offshore. And there's also a difference between the north and the south. And apparently that doesn't really fit to the amount of earthquakes. So where we have the higher slip, we have less aftershock seismicity than in the south, where the earthquake rupture was less intense. And the big question is what conditions this aftershock seismicity, and how can we constrain the controlling parameters, and what can we learn about that? A very simple and basic answer to the question what causes these aftershocks is the stress change that is caused by the main megathrust event, by the Tohoku earthquake, or more precisely the stress drop in the earthquake. So the stress drop describes a change in shear stress along the plate boundary fault, and it is believed that this shear stress scales somehow with the amount of slip. And in the main slip area, we have an effect that is called post-seismic weakening or velocity weakening, and it decreases the shear stress on the fault, which allows the rupture to propagate. And with the decrease of the shear stress, we also decrease the compression in the overlying forearc. And then you have the boundary regions here of the slip area in which the rupture is arrested. And in this area, we have a post-seismic strengthening and an increase in shear stress. And that increases the compression of the forearc. So overall, this stress change along the plate boundary fault changes also the stress in the overlying forearc. And if we want to understand the aftershock seismicity in the forearc, we must understand this stress change, because it shows us what changed and what is the seismic reaction. One issue with that is that this kind of stress drop calculations give you just an information of relative change in stress. It just tells you that the stress either increased or decreased, but we don't know what was the exact value of stress before the earthquake and what was the value of it after the earthquake. So we have, if you represent it in kind of a Moore circle diagram, we know we have a preseismic state of stress and a post-seismic state of stress, but we don't know the magnitudes. And we cannot tell you if it was like this or maybe like that. And this doesn't help us to understand this distribution of aftershocks. What we really want to know is something like this, where we have the absolute magnitudes of stress and we know how close the rocks are to failure. So as a representation in the Moore circle diagram. And in my talk today, I present you a simple mechanical approach, how we can approximate the stress conditions and get a very fairly idea about the absolute stresses in the forearc before and after the earthquake. We start with some consideration of what controls the stress in the forearc, and there are actually mainly two factors that control the large-scale stress conditions, or the first-order stress conditions. The one is we have a topographic gradient between the volcanic arc and so the high mountainous area and the deep oceanic trench. And this gradient causes also a gradient in potential energy, and this causes tension in the forearc. It induces, so to say, a tendency to gravitational collapse. And this is counteracted by shearing and friction along the plate boundary fault, where the shear stress along the megathrust causes compression in the forearc. And you can see that the shear stress on the megathrust scaled with this parameter mu, which is the effective friction coefficient of the fault. So a higher friction coefficient means a higher shear stress and then a higher compression of the forearc. And this relation is shown now here, so we can calculate the differential stress in the forearc as a function of the effective friction coefficient of this plate boundary fault. And of course, we can also look at the state of stress in terms of plunge of sigma 1. This is shown in the other diagram. I come to that later. If the friction coefficient would be 0, then also the stress on the fault would be 0. And the forearc would only experience the tension due to the gradient in potential energy. And you can see that here, at this case, you see two solutions. One is calculated for a location within the wedge, and one somewhere within the arc region. We have differential stresses in the forearc at some tens of megapascal, and the stress conditions are tensional. So we have a steep orientation of sigma 1. And as the friction coefficient increases, the compression due to the shearing along the megathrust increases, and then you first reach a point where the stress goes down, and then compression becomes dominant and increases, and we build up high stresses under a compressive stress regime. And accordingly, sigma 1 with this evolution is rotating towards the horizontal. So, given any kind of stress condition somewhere within this diagram, forearcs would be normally not at failure if we assume a normal rock strikes. For frictional failure, for seismic failure within the forearc, we need that the effective stresses are reduced. And this is illustrated here again in a more circle diagram where we have the normal stresses and the shear stresses. The circles indicate the differential stress. This would be the total stress. This is the failure envelope, and failure occurs only if we touch this line. And this is our state of stress, and we need to reduce the effective stress, which is commonly explained by the effect of pore fluid overpressure. If we know the total stresses, we can calculate the this parameter here, which gives you the effective friction coefficient for faults in the forearc, for which these faults were at failure, for which these conditions would be met that you see here on the left. And if with an earthquake the differential stress changes, then also this parameter, this effective friction coefficient changes. It is not a real friction coefficient of a given rock, it is just an indication of the friction coefficient that we would need to ensure that the rocks can be at failure. So, if the stress changes, this value changes, and this change can be in two ways. Either in a way that it destabilizes the forearc and supports failure, or in a way that it stabilizes the forearc and prevents failure. And this is just dependent on this relation of these two values. If for the stress conditions after the earthquake, this value is lower than for the stress conditions before the earthquake, then we have a stabilizing effect. We have a stabilizing stress change because the pre-seismic stress conditions would be more favorable for failure and seismicity than after the earthquake. This is a graphic representation. If this is the state of stress before the earthquake, and the blue circle gives you the representation after the earthquake, then you see we move away from the failure envelope. And on the other hand, if this value is of μc is larger after the earthquake than it was before, then we destabilize the fault. And you will see in this case, we would even cut the failure envelope if the fault was before critically stressed. And at this condition, the fault would be unstable and needs to deform to get back to a critical or stable state. So what we can do is we can calculate a stability parameter. I call it here C. And this parameter is nothing else than comparing the difference between this mu value that we calculate, and it is normalized to the pre-seismic mu value. And as such, we can say, okay, if this value is larger than 0, then we have the stress change destabilizes the forearc. But if it is smaller than 0, then it gets stabilized. And now what is difficult to see actually here is the gray area. And these yellow dots are indicating aftershocks. All the aftershocks that we see should locate within the area that gets destabilized, not in the one that gets stabilized. We need that the stress changes favors rock failure and seismicity. So what we can do is we can calculate the distribution of these areas in the forearc that get destabilized as a function of how the effective frictional strength of the megathrust changes in the area where there's a stress drop and a stress increase. And to do so, we used a finite element model that calculated the elastic stresses in the forearc. And I don't want to get lost too much into the model setup. It is basically very simple. We have two plates in a frictional contact. This would be here the frictional contact. We have a plate that goes down. And we can assign the effective frictional strength to the megathrust, so to say. And we can define different segments of this fault that can then experience, for example, velocity weakening or post-seismic weakening and post-seismic strength. And then we have an upper plate that is elastic. We account for water load and for gravity. And for these conditions, we calculate the stress in the forearc. And before we apply this approach to Japan, I would like to show you some generic model results in which we took a setup for an arbitrary forearc. And each model run includes a pre-seismic step and a post-seismic step. And the difference between the model runs is the effective friction coefficient applied to the megathrust. And this mimics the effects of velocity strengthening and velocity weakening in the earthquake. And we did different model sets where we choose different pre-seismic values for the friction coefficient of the megathrust. So we use two very low values, 0.025 and 0.03, and then slightly higher values of 0.06 and 0.09. And with that, we change the pre-seismic stress conditions in the forearc. And for the post-seismic state, we apply in all models a low effective friction coefficient of 0.01 to the weakening segment of the megathrust, which ensures that the forearc experiences tension post-seismically, as evidenced by normal faulting. And along the strengthening segment, the deeper part of the megathrust in this case, we increase the friction coefficient by 0.01. So, for example, if we have a pre-seismic value of 0.03, then it becomes 0.04. And then, for all these changes in friction coefficient, we calculate the stresses, and from that, we calculate the stability parameter that I mentioned before. And these are the generic model results, which is a bit busy, but I explain this plots here. So on the x-axis, we have always the distance from trench. And here you would see a cross-section through our model forearc. We have here the volcanic arc region. This would be the coastline. And then you can see the extent of the post-seismic weakening segment and of the post-seismic strengthening segment where the stress increases along the background of the fault. And then these different gray-colored areas mark the extent of the areas in which the stress change tends to destabilize the forearc. And on the other graphs, I calculated average values for the crustal part, so for the upper 30 kilometers within the forearc, of this stability value to give you a better idea how it changes across the forearc, and of the orientation of sigma 1 for the pre-seismic state, that are the black curves, and the blue curves for the post-seismic state, and the average change in differential stress within the forearc clusters in the upper 30 kilometers. Maybe you see that for the post-seismic state, within 150 kilometer distance from the trench, that is approximately the down the limit of the weakening segment, the orientation of sigma 1 is identical for all the different model runs. And this is because for all models, the value decreases to the same value, to 0.01. And you can see that we have this tangential stress conditions because this value is larger than 45 degrees. For the preseismic orientation, it varies because we vary the preseismic value of mu. Now you can see if we have a preseismic mu value of 0.09 and it drops to 0.01, then the entire forearc remains basically stable. So we have unfavorable stress change for any aftershock seismicity. And this you can see here, if you look at this stability parameter, it is always below zero, that is the dashed line. If the preseismic mu value is 0.06, we have different stress conditions, and there's a small part where this value gets above 1, and this is this area shown up here. And we have a small patch where the stress change would be suitable for aftershock seismicity. And as this value becomes smaller and smaller, the area in which we have the right stress change to trigger aftershocks increases and increases, which you can see by these larger gray areas outlined above here. And then you can see that there's even a big difference between a value of 0.025, in which case also there's some instability underneath the arc region, and 0.03, which is missing this region. And surprisingly, if you look at the absolute stress changes here, if we have very small preseismic, a very low strength of the megathrust in the preseismic periods, the overall stress changes are very small, maybe about 10 megapascal, that the differential stresses increases or decrease. But these are the stress conditions that are favorable for triggering aftershocks. If you have a large stress change for the other models, like here, stress changes of up to 100 megapascal, this large stress change is not favorable. Basically, maybe to illustrate that, sorry, I go back, because you end up with something like this. So what we see is that the extent, the spatial extent within the forearc of areas that experience a stress change that is favorable for triggering aftershock seismicity is very sensitive on the effective frictional strength of the megathrust before and after the earthquake. This means we can reverse this approach and take the natural distribution of aftershocks and determine for which pairs, for which pre- and post-seismic stress conditions we would get a distribution or occurrence of unstable fields that matches this aftershock distribution. So basically, we can invert the aftershock distribution for the pre- and post-seismic stress conditions. And we do so, and this is a approach that we apply to Japan. And what we have as an additional information are the focal mechanisms that indicate us the state of stress in the forearc. And of course, our models must agree with the state of stress that is indicated by the focal mechanisms. So to apply this to Japan, we constructed additional finite element models that were then really tailored to the setting of Japan, in the sense that we respect the specific topography and the slab geometry and the water load and the crustal thicknesses. And then we constructed two different model sets. One model set that crosses here the northern slip area across Sendai, and one model set for the southern slip area across Iwaki. And then we try to find the best fit solution, in which we encompass most of the aftershock solution within areas that experience a favorable stress change. And these results are then counter-checked against the stress information that we get from the focal mechanisms. And here you see the results for Japan. These are, the left one is for the northern, for the main slip area, and the right one is for the southern slip area. And these red lines here, they outline the destabilized areas of the forearc. And actually, this is also gray filled, but I think it is difficult to see. But what you can see is that all these dots, which are the aftershock seismicity, most of these events plot within the destabilized areas for this best fit solution. It's about 98% or something like this. But there are some parts, for example, these events appear that are not included in it. And we don't want to overfit the model. One could also get them included, but then other parameters are less reasonable, so we don't want to do that. Before I address this stability pattern in more detail, I also want to give you an idea about the absolute stresses that we calculated for the pre-seismic and post-seismic period. This is shown as differential stress within the forearc, again for the Sendai transect and for the Iwaki transect. And the scale is here between 0 and 140 megapascal differential stress. And you see that we have mainly these very light colors of gray. So the differential stresses are overall very low, some tens of megapascal. And only close to the plate interface, we have some higher stresses of up to 120 megapascal. So, and you can also see that there are some subtle changes in the differential stress between the pre-seismic and post-seismic phase, and also between the models. But these changes are overall very low. And then there's all this mess of numbers here. We don't need to worry too much about it. It basically indicates you the friction coefficients that we use before the earthquake and after the earthquake. And the other numbers here indicate you the stress change that results from this. And these are always something around 10 megapascal, which agrees with stress drop estimates for megathrust events. Here you have a similar kind of information. Now it is calculated the stress change between the pre-seismic model and the post-seismic model in differential stress, also in megapascal. And where you see the blue colors, we have areas where the stress decreases. And where you see the brown and green colors, we have areas where the stress increases. And you can see this is very different for Sendai, for the northern profile, and for the southern profile. But the overall values are very similar. And here you see again average calculated for the upper 30 kilometers within the crust. If we plot on that the occurrence of aftershocks, then you can see that most of the aftershocks, all these gray dots here, occur within areas where the differential stress actually increases after the earthquake, which makes sense because the stress increase is always favorable to destabilize rocks. We can also look at the stress change in terms of orientation of sigma 1 and compare to the focal mechanisms. So the blue dots here indicate the normal faulting that we observe in the upper plate. In black is the pre-seismic orientation of sigma 1. You see for the pre-seismic state, most of the forearc is under compression, except for some small areas here and also in Sendai here. And post-seismically, for the main area, the first 160 to 170 kilometers of the forearc are under tension, and this fits also the extent of the normal faulting meters. For the southern slip patch, the situation is quite different. The tensile stress conditions reach underneath the arc area. And you can also see that the extent of the normal faulting events is much higher. And here, where we get the first thrust fault events, again, the stress conditions are also again compressive. So this plot summarizes as again this distribution of stability on top again. Here you also see now the value of the stability calculated again for the crustal average, for the main slip area and for the southern slip area. And you can see that there are some differences and similarities. The differences we see that here, very close to the trench, we have relatively high values of this parameter C, which would mean that there the conditions are very favorable to drive aftershocks. And then it decreases landward, and it is very close to zero in the interior part of the forearc. And you can see that also that basically only half of the crustal volume here has anyway destabilizing stress conditions. For the Iwaki transect, it is a little bit different. We have not this very high values close to the trench, but more in the interior part. And you see it goes a little bit up and down. And where we have the ups, we have also the most intense aftershock seismicity. And then towards the interior part of the forearc, it becomes stable or again normal. This stability value calculates from this critical friction coefficients for the forearc crust, which gives you this indication for which or what friction coefficient is required in order that the faults can fail at the given stress conditions. So I give you here the pre and post seismic values, and there is again this difference that the pre-seismic values are very similar for both transects, and these are values generally about 0.05 or even less. And the post-seismic values are much higher for the main transect than for the southern transect. So in principle, in this area, we could activate much stronger faults than in the Iwaki transect, but we see actually the lower seismic intensity here than in this case. And how we interpret this is that this reflects the differences in co-seismic slip. So here you see co-seismic displacement that are modeled and original GPS data and the co-seismic slip. And you see that we have very large displacements where we have the high slip close to the trench. And what this causes is that the forearc gets dilated. You have dilation of the forearc. And if you have this dilation, you would drop the pore fluid pressure, which would increase the strength of the fault. So what we think is that this very high values here that we have, but the low seismic activity is actually representing the dilation of the forearc. And in the southern part, we have much smaller co-seismic displacements, and we have also no or very little slip close to the trench, so the forearc gets not that dilated. And we think this is why we have this broader intensity. And then the very low seismicity inland that we observe in both cases is basically because the stability changes, but mostly any seismicity in this area would require that the strength of the fault is almost zero. So in the outer part, we can activate stronger faults than in the interior part, because the stresses are not high enough to activate stronger faults. This is the modeling part, in which we now claim that we have a fairly good understanding of the stresses in the forearc before and after a great subduction megathrust earthquake. How can we test this finding? It's a bit tricky. What we would need to do is to measure the stress in the entire forearc, and we cannot do this. So what we can do is to look at the stress that is released within the forearc seismicity. So each of these little earthquake that occurs within the forearc releases some stress. It's also a stress drop. And the stress drop released by an earthquake can only be equal to or smaller than the stress on the fault. So it must be actually smaller than the background stress, or it can be equal if you have a complete stress release. Stress drops are often calculated. We find much about that in the literature. They often show a log normal distribution and span a relatively wide range of values, somewhere between less than 1 megapascal to up to 100 megapascal. So it's always good to look at them a bit from a statistic point of view. And typically in the literature, these stress drop values are evaluated without any background knowledge about the without any knowledge about the background stress field, or without having a good idea about absolute stresses. But here we have now the model stresses to which we can compare them. We looked at the stress drops in the Japanese forearc before the earthquake and after the earthquake. And on the x-axis, you see the stress drop estimated as megapascal, and you have the depths. And this is logarithmic because the stress drops show this logarithmic log normal distribution. And the gray dots are the events, are the estimates for the individual events. You see we have about 800 stress drop estimates for the time before the earthquake and about 5,000 estimates for the time after the earthquake. And the white squares with the bars indicate you the mean stress drop value for depth intervals of 10 kilometers, and the depth intervals overlap by 5 kilometers. And the standard deviation of this mean value. And you can see that the trend for the conditions before the earthquake and after the earthquakes are very similar. And we see a subtle depth dependency where the stress drops increase from 2 megapascal up to 8 megapascal. And this is true before the earthquake and after the earthquake. And these lines here give you now the maximum shear stress that we get out from the model as a function of depth. And you can see that the blue line is for the northern model that crosses the main slip area, and the red one is for the southern model. You can see there are subtle differences, but overall they show a similar depth dependency. And these dashed lines here are 10% of the maximum shear stress values that we get out from the model. And you can see that, I mean, before I showed you, we have very small stress changes, and on average, the stress in the core does not change much. This is represented by the similarity of these lines. And you can see that the mean stress drop values always follow approximately this 10% value of the maximum stress. And you can also see that the maximum shear stress that we get out from the model always encompasses the entire range of the individual stress drop values. So we think that this is actually representing that this, it's first of all confirming that we have a good idea about the stress conditions in the forearc, and that the stress drops release on average something of about 10% within the forearc of the background stress. The diagrams that I showed you before were for the entire forearc region. We can also look at subsections, for example, the submarine forearc in the main slip area, which shows you here, and it shows the same relationship that I explained before. It's also true for the southern area. You see here only the stress drop estimates for the south, and we have again the same relationship to the model stresses. And we also looked at Basel events that are events that occur within 5 kilometer distance to the plate interface, because there we cannot say if they are on the plate interface or at the base of the forearc. And so we looked also separately at them, and we calculated also the stresses at the base of the forearc, and we find again that there's a very good agreement between the stress drop values and the model stresses. So we think that our stress estimates are really robust and represent pretty well the conditions in the forearc. So to summarize all this, what I presented to you today was a new approach to determine the stress drop in the megathrust earthquake, the absolute pre- and post-seismic stresses, so we don't look only at the relative stress change, but at the absolute stress change. And we can also infer the frictional properties of the megathrust and of faults within the forearc. And I think the particular aspect of all this is that we do it all with one relatively simple model. Normally, you would have for each step different models that are based on different mechanical principles and assumptions, and that all generate conflicts between each other. And instead, we find that there's actually a really good agreement between our model results and the geophysical data. This summarizes a little bit the things that I said before. A broad occurrence of aftershock seismicity requires that the stresses in the forearc are very low before and after the earthquake, and that the stress magnitudes are also very similar. As you can see it here, we have very subtle variations in stress. And these conditions, if you remember this diagram before, are only given if we have a really extremely weak megathrust before and after the earthquake. At these conditions, if the absolute stresses remain similar, then all the seismicity is mainly controlled by the change in the state of stress as we get to a normal faulting regime or more tensile stress regime, but not so much by the stress magnitude. And this also implies then if the stresses are so low, the weaks and the faults in the forearc must be extremely weak. The differences that we see in the onshore and offshore part, I mentioned that before, are mainly controlled by the different stress conditions here, which require that faults in the forearc have almost absolutely no strength to become active. And the difference between the north and south that we see in the intensity of the aftershock seismicity, we interpret that this is actually just for sure reflecting a difference in rock strength. But we think this is not a permanent difference in rock strength, but a particular effect of the dilation of the forearc. So, outlook. I think the main question is maybe is this does this general apply, and can we use that also for other margins or not? And the model results that we have, they indicate the low stresses, but in particular they also indicate that the stress in the arc region here, where the topography is highest, is less than 20 megapascal. And these stress conditions are actually inferred from force balance analysis of global subduction zones that look at the stress state in a forearc averaged over many, many earthquake cycles. And what this force balance actually is looking at is the relation between the gravitational stresses controlled by the margin relief and the megathrust shear stresses. And it predicts that the height of mountain and mountain belts at subduction zones is actually exactly at this limit where tectonic forces can drive it. And if you are at this point, then the stress underneath the highest elevation must be very low. I studied that in a previous study where we now are not really addressing the stress here, but we look at what is the elevation of mountain ranges that can be tectonically supported by the forces acting at the plate margin, and what is the elevation that we really observe, and it plots almost along a one-to-one line. What is interesting for us is that the uncertainty within these values translates to a stress difference of about 20 megapascal. So what this means is subduction zones should generally evolve to a state where the stress underneath the forearc, the differential stresses are not higher than 20 megapascal. If this is true, then we can use this stress constraint from the long-term force balance as an indication for the preseismic stress conditions and predict from that, or estimate at least, which parts of the forearc may become unstable during an earthquake. So we can change these approaches, mechanical approaches that I presented today, another time. And we did that now for an earthquake where we can also test that again. It's a Chile, it's a Maule earthquake in Chile. And I make that very quick. We have again the long strike differences in the aftershock seismicity and also in the slip distribution and all the things. And we did this model starting from the long-term force balance and applying a homogeneous stress drop along the plate boundary fault. And we get a very different stability pattern in the upper plate, which again matches the characteristic differences in the aftershock seismicity. Here, everything was focused in the offshore forearc, in the submarine part of the forearc. And in the other case, that is the model for the northern part, we have all this aftershock seismicity in the coastal region and strong normal faulting. So what we think is we have a relatively good idea of how to describe for global subduction zones where aftershocks may occur in the upper plate. And with that, I'm done, and I thank you very much for your patience and interest.
Well, thanks a lot for your presentation. Are there questions in the audience? If people need a bit of time to think, I actually have one right now. You said that the driver of, or the main change in input parameters for the models that allow you to predict where the upper plate stabilizes or destabilizes is the co-seismic change in the friction coefficient of the wind. Do you think that change is only co-seismic? Because what happens is, yes, you have the earthquake, you basically break the whole interface, but then after the earthquake, you have post-seismic creep that probably continues an earthquake of that size for several years and probably amounts to something like several decades or so. Does that also have an influence on the friction coefficient, or would you say it's really purely co-seismic as instantaneous?
No, I would actually think that it is that afterslip and also aftershocks in the plate interface also play a role. The big change in stress occurs co-seismically. And afterwards, I think we have smaller stress changes due to the processes that you addressed. And for me, the main reason to think so is, first of all, it seems a little bit logical that they also affect the stress state. But what we see is that, I mean, we look at elastic changes in stress, which are, if they would be really purely elastically, they would be, so to say, instantaneously. But the aftershock seismicity evolves through time. So some of the, like the Pichilemu earthquakes in Chile, they came about 2 weeks after the main shock, and in Japan we had also strong normal faulting events about a month or even some years after the main shock. So I think there's a continuous weakening that is going on, and that has an influence on also the temporal evolution of the aftershock seismicity. What we see in the models is that if you just change locally on a small scale, the friction coefficient, it has almost a negligible effect on the stress state in the upper plate. So you need really this big post-seismic effect, and afterwards you can modulate it.
Questions from the audience? Well, in that case, we'll just leave it at that.
Yeah, okay, good.